All right, we'll go ahead and get started. For those of you in attendance, thank you for your time and for joining us today. My name is Enrique Garcia, and I'm an applications engineer here at GoEngineer, specializing in our simulation products. Today we'll be talking about some of the ways we can process our SOLIDWORKS models in preparation for running simulation studies in our designs. We will also be covering some tips regarding simulation study management. Before we begin, I just wanted to give you a little bit of background information about myself here, just some highlights. Our webinar today will be broken up into two main topics: model processing or editing, and model organization. Model processing will involve topics on how we can alter the model so it's optimized for the use in simulation studies. The second topic will introduce utilities for SOLIDWORKS functionality that can help manage your models when using SOLIDWORKS simulation. Also, this presentation is intended to help streamline your SOLIDWORKS simulation studies, but most of these tips and tools can also be applied for use in the preparation of your models for SOLIDWORKS flow simulation as well. Also, feel free to ask any questions during the presentation. We'll try to answer as many questions as we can as we go along, and we'll also have some time at the end of the presentation for any additional questions. So let's begin by touching on some of the ways we can process or edit our models for simulation. When preparing a model for simulation, it's a good practice to simplify or defeature your model. This will save on calculation time and computational resources for any future studies. It's important to test what features we should leave or remove, and the process is largely trial and error or obtained from prior experience with working with your models. Simplification of your model is mostly done by defeaturing your design. Defeaturing your design can be done by deleting aspects of your model, but this can be damaging to your design and cannot be easily reversed in most cases. Because of this, we can use the Exploded Views tool to easily separate the model and suppress aspects of your design that are negligible or are not structurally significant. This will help concentrate our computational resources to be more efficient with simulation. Let's talk about Exploded Views, a SOLIDWORKS functionality that we can use to set up your model or use for accessing difficult-to-reach references in your models for simulation is to use Exploded Views. Now, this is just the regular SOLIDWORKS Exploded Views tool functionality. When trying to set up a simulation study and select hard-to-reach selection entities, this can be an easier job if we can quickly explode the model so that components are easily accessible. Some typical scenarios of when to use Exploded Views are when trying to select small or hidden components, when setting up an external load, or another scenario is when selecting coinciding or closely packed surfaces when assigning contacts, or any other constraint or boundary condition while setting up your simulation study. Easier selection of entities could potentially save much time when setting up multiple simulation studies using that same model. There are two major ways you can create exploded views in SOLIDWORKS. First, from the main Insert menu pull-down from the top right of SOLIDWORKS, and the second way from the Configuration Manager by right-clicking on the desired configuration and selecting New Exploded View. For those of you that are new with SOLIDWORKS Exploded Views, let's do a little quick introduction. Here we have a simple 3-component assembly, and let's create an exploded view. We'll go up to the Insert main menu in SOLIDWORKS, and we'll come down to Exploded View. This will launch the Exploded Views Property Manager. Now, the workflow to apply Exploded View steps is you go in and you select the component desired to explode, and you can use the UI or the arrow here to move and drag the model to the desired exploded view length. You can snap to the different notches on the ruler as well. You can also enter more discrete values under the fill-in field here. Once you're done manipulating the first component, click the Done button to add the first exploded step. Let's move another component before we continue. I'm going to click on that second plier arm there and just eyeball a nice little explode distance. Click the Done button. Just a simple 2-step exploded view. If your models are rounded or can be a turned part, you can also explode using the radial step component instead. Now that we're done, let's click the OK check mark, and let's access our exploded view. I'm going to click on the Configuration Manager tab, and under the default configuration, we have a derived configuration for our exploded view. By right-clicking, I can go and collapse, or I can re-explode the design at any time. Now, the most popular way to defeature your model for simulation is to use the suppress functionality in SOLIDWORKS. You can suppress parts of your model from any level in your design, from sketches and features all the way up to full parts and subassemblies. When you suppress something, you're essentially deleting it with an option to bring it back. This is what I like to call a documented deletion, because there's a gray reference that is left of the feature or item that you suppressed that can be acted upon to unsuppress or bring back the features and items. Anything that is suppressed will not be included in the simulation study. Now, if you want to temporarily remove something and still keep it in the simulation study, then I recommend using the hide show functionality instead. There is an automated way that one can suppress aspects of your design with the help of using the Simplify utility. This tool is located in the Analysis Preparation tab when you're working with part files, or can be accessed from the Tools, Find, Modify submenu when you're working with assemblies. Once the utility is turned on, you can specify if you would like the part to be simplified by reviewing individual features of a design, or by the general volume of the model. Simplification occurs by suppressing the collected features or regions detected by the Simplify utility, and can be specified to create a derived configuration to organize the changes, leaving your original and default configuration intact. Let's go through a quick workflow to showcase the Simplify utility next. If I have a simple part file here, or any part file in general that you want to simplify for simulation further, and you have the simulation add-in checked on, you'll have an Analysis Preparation tab in the Command Manager. Under this Analysis Preparation tab, you're going to have the Simplify utility. Let's click on that utility, and then the Property Manager will show up on here on the right-hand side of the screen. Now we have some settings here to specify features, a simplification factor I can move up or down for sensitivity, and a detection mode of either choosing feature parameters or volume-based detection. So I'm going to choose feature parameter and choose Find Now. And the Simplify utility will select and collect the different features that I could potentially remove from this new configuration I'm about to make. A similar workflow can be done when you're using the volume-based simplification factor. When I click Find Now, the software will go in and looking at the volumes will pick up the features that define those specific volumes, in this case the whole part file. And then we'll select the individual features that I can go and remove from my design. Holding the Control button, I'm going to select a couple of these features. I'm going to make sure the Create Derived Configuration is on and give it the default name and click Suppress. If I navigate over to my Configuration Manager, I can now see that I have the derived configuration active with my more simplified version of the part. Another way one can address or process their models for simulation is with model idealization. Model idealization is the process of taking a more detailed or complicated geometry or portion of design and simplifying it by either replacing full components or portions of the model with completely different and simpler models, or using other various techniques we'll show here in a moment. Replacing one component for another is pretty self-explanatory and involves deleting or inserting its replacement manually, or one can also use the Replace Components feature from the right-click menu in the Feature Manager design tree. We will introduce two interesting idealization functionalities that perform model idealization both automatically and during the actual calculation of the solution. These are Convert Toolbox fasteners to bolt connectors, and the use of sheet metal and weldment components in the simulation study. Convert Toolbox fasteners to bolt connectors is a capability that will take any toolbox fastener and will convert it into various virtual bolt fasteners and features in the simulation design tree. During the conversion process, simulation will take all the information regarding the geometric features, location, and material of the toolbox components and will automatically map them internally to generate the appropriate bolt connectors. If appropriate, a preload is also generated during this process. Since the conversion tool maps specific metadata for each toolbox component to the simulation feature, only official toolbox components are supported. This conversion tool is simple and only requires one click to implement. After the connectors are generated, one can review or edit their options and settings as regular bolt connector features within the simulation design tree afterward. To implement this functionality, one can click the option Convert Toolbox Fasteners to Bolt Connectors during the creation of the study, or if the study has already been created, you can also right-click on the Connections folder and select Toolbox Fasteners to Bolts in the Simulation design tree. It's important to note that this capability is included for installations with licensing of Simulation Professional or above. One last note about this tool is that this conversion process can only be used once per simulation study, so it's a good idea to include all the toolbox fasteners needed before working with the simulation study and using this process. If you forgot a couple of toolbox fasteners, a workaround to this limitation is to create a new study and simply copy over by clicking and dragging all of your setup components and constraints to the new study so that the option is available for use once again. Let's show a quick demonstration using the Toolbox Fasteners to Bolt Connectors functionality. Here we have a model with a couple of toolbox fasteners, nuts, and bolts. And we're going to start a new simulation study here at the very top. We'll click New Study. And during the initial creation of the study, we have an option that reads Convert Toolbox Fasteners to Bolt Connectors. When I choose this, the simulation study will automatically collect those toolbox fasteners and then convert them to our bolt features in the study. Let me cancel out of that. And I have an existing simulation study here that I want to initiate this functionality for. So let's say that you've already created the study and you wanted to recycle these toolbox fasteners and create them into virtual fasteners or bolts like you see here for these foundational bolts. To do this, you're going to right-click on the Connections folder and then choose Toolbox Fasteners to Bolts. And that's it. The tool will give you a summary of what happened. I'll click OK to accept the summary. And now you have a new folder here with your virtual fasteners. And they can be edited just like regular bolt fasteners, just the same. The other form of idealization occurs automatically during the creation of the study when you're using either a sheet metal or a weldment component in your simulation study. When a SOLIDWORKS part file is either converted to a sheet metal component or was created using the sheet metal features in SOLIDWORKS, it gains foundational sheet metal metadata, such as thickness, bend allowance, and auto relief information. This data is then stored in the sheet metal feature at the beginning of the feature manager design tree for the part file. When a simulation study is then created using the part file, simulation will automatically assign the use of shell elements for mesh creation and will also already know the exact thickness of the body, which is needed when running the calculation. There's no need to manually assign that thickness. The same is true when you're using weldment components. When a simulation study is created with weldment components, beam elements will automatically be assigned to each weldment. Just to show a bit further, simulation will automatically pull the thickness of the shell definition from the sheet metal feature and will idealize the thickness of the shell element internally in its calculation. And so a similar thing again happens with weldment components as shown on the left side of the slide here. Weldment components will idealize the cross-sectional area of the geometry for its calculation, and will use a simple beam element for its calculation across the length of each weldment. If you don't want the use of beams and shell elements, you can easily convert the bodies back to solid elements in the study. Switching between shell and beam elements and solid elements is driven from the parts folder in the simulation design tree, as shown on the top right picture on this slide. If you're interested in learning more about shell and beam elements, these topics are covered in pretty good detail in our Simulation Essentials course. If you're new to simulation or have not used SOLIDWORKS simulation in a while, I highly recommend it. I'll add my email at the end of this presentation if you want to learn more about the simulation courses we offer here at GoEngineer. Before we continue, I just wanted to illustrate how when you're working with SOLIDWORKS weldments and sheet metal components, how these are treated in SOLIDWORKS simulation automatically. Here we can see our frame is made out of a weldment structural members, and part 2 is just a simple sheet metal design. I'm going to go ahead and create a new static study. If I expand the parts folder, you can see now that under the frame we have a setup of our cut list with all of our structural members, and each of them has their own weldment or beam element now assigned to each one. I can right-click and I can see that they've already been defined The same thing goes for my sheet metal part. And we can see the thickness of the sheet metal part has been automatically pulled from the sheet metal feature from the actual part file definition. If you wanted to treat a particular body as a solid once again, you just simply right-click over the body and you choose Treat as Solid. The body is once again treated as a regular solid body in simulation. If you wanted to revert it back to a beam element, just once again right-click over the body and say Treat as Beam. And that part file segment is once again treated as a beam element. Now that we've covered best how to defeature and idealize your simulation models, let's talk about how we can organize and access these items for easier access in simulation. For this section, there are 4 major items I'd like to review with you that will help with the organization of your SOLIDWORKS models. These are working with configurations, working with selection sets, pack and go, and interference detection. Since simulation studies are assigned to the active configuration upon the creation of that study, configurations are a great way to keep all your defeatured and idealized items organized and assigned to your simulation studies. Before creating a simulation study, it's a good practice to create a configuration that's made up of all the suppressed or replaced items in your model, so that's easy to access for your current and future simulation studies. To keep organization as simple as possible, I avoid creating a derived configuration and stick with just creating a top-level configuration, and I name the study something like FEA, Simulation, or just the name Simplified. Also, under the advanced options, make sure you checkbox the option Suppress New Features and Mates. This option will automatically exclude any new features and mates and assemblies added to the design tree while other configurations are active. If you check this option on, this will help protect from any unwanted or unanticipated feature changes to the simulation version of the model. Desired features can then later be manually unsuppressed for our simulation configuration if needed. Here's an example of an assembly from a medical device that used configurations to create a static study from. If I navigate over to the Configuration Manager tab and I activate the FEA or Simplified configuration, we can see all the components that were removed or suppressed from this particular configuration in the feature design tree. If I jump down to the Static 1 study on the lower left-hand side of SOLIDWORKS, we can see the actual study setup and some of the preliminary results from this particular analysis. If I go back to the Configuration Manager tab and I edit the properties of this configuration, we can see under Advanced Options that we used Suppress New Features and Mates. Again, this kind of draws a line in the sand or protects you from any new features or parts that are included in this assembly and will automatically suppress them unless you want to go in there manually and unsuppress them and include them in your own FEA analysis. Another SOLIDWORKS tool we can use to make our simulation experience a bit easier for organization is to take advantage of the Selection Sets tool in SOLIDWORKS. Selection Sets is a way for SOLIDWORKS users to save and organize and to call upon one or more groups of selection entities, whether it be a set of points, edges, faces, bodies, or a combination of those entities. Selection Sets makes the logistics of selecting many difficult-to-select entities easier, especially when they'll be selected for many different circumstances. With using Selection Sets, you'll make that difficult or that meticulously time-consuming selection of entities once and save it so that it can be reused at any time. To create a selection set, you will highlight the entities by doing a Control Select, and then select the combination of those selection entities you want, and then right-mouse click to select New Selection Set from the right-click menu. We can then rename and manage all those saved selection sets in the Feature Manager design tree under the Selection Sets folder. Saved selection sets can then be used to populate any property manager, including those in simulation. And this way you can quickly add or populate these chosen selection faces for a force load or a fixture definition, for example. Let's go back to SOLIDWORKS and showcase how we can use selection sets. So here we have a model that has an exploded view, but it also has 2 saved selection sets in its design feature tree. We're going to be using these selection sets to populate faces for force values inside of the static study here below. Let me go in and create a new external load here, and we're going to choose pressure. Now for my selection box, instead of going in and choosing all the individual faces, I'm going to navigate over to my abbreviated SOLIDWORKS design tree and select the first selection set. This will pick up 10 individual faces from the model automatically within a split second. I'm going to make sure my directions are pointed in the appropriate direction, and now I've created a quick pressure on the design. The implementation is very, very straightforward, and the actual creation of selection sets are easy as well. To create a selection set, you simply hold down the control button and mass select the different faces, entities, or points that you'd like to include in your selection set. And then you'll do a right click right afterward, and then you'll choose Save Selection and choose New Selection Set. If I navigate up to the SOLIDWORKS design tree, we can see our new selection set here that can be managed in the Selection Sets folder. Speaking of SOLIDWORKS tools, another organizational tool is the SOLIDWORKS Pack and Go functionality. Pack and Go is created to take a full model or family of SOLIDWORKS files that have interconnected references and allows them to be copied or duplicated into its own separate environment or directory while keeping all references intact. This is an option I have seen many simulation analysts take, especially if they are working with live data that is in production, or they just don't want to risk causing any changes to the current design or changes to the file metadata for the sake of their file management system. The Pack and Go functionality can be accessed both from within SOLIDWORKS from the File main menu pull-down, or from the regular Windows File Explorer by navigating and right-clicking on the assembly that you want to duplicate, and then choosing Pack and Go from the SOLIDWORKS category. As shown on the right-hand side of the slide, some best practices for when using Pack and Go for simulation is to add a prefix with an indication such as FEA or something similar, so that all files of the new copy will be renamed to that particular prefix. This will ensure that we have unique file names for this new copy of the model, and will give us some assurance that the file references won't cross-mix with the original model files. I like to also flatten my export to a single labeled folder and include any existing simulation results if they're important. Once I have my separate Pack and Go for the model, I can then make sure that I close all other original files and then begin to defeature, delete, and start my process for my model preparation for my simulation analysis. The last tool I want to review with you all for this last section is checking your model for any model interferences. CAD geometry can easily be created in interference with other model bodies, or also when there is a translation error when the model is imported and translated from one modeling kernel to another. If a model with interfering bodies is brought into simulation, this can cause errors in the calculation of the mesh or instability in the calculation of your solution. SOLIDWORKS includes a utility called interference detection that checks for these model body interferences. The interference detection tool is for interrogation only and will simply detect interferences. It won't resolve them. Once we detect interferences, if we expand each detected line item, we can select and highlight the components that take part in the interference. We can also detect and highlight the common volume of the interference. Once these areas are spotted, we'll need to use regular SOLIDWORKS modeling techniques to resolve the interferences on our own, and then recheck for the interference again. Another tip for using the interference detection tool is that you can use the option Treat Coincidence as Interference to detect how many touching face pairs exist in your model. Since addressing contacting face pairs is one of the more crucial steps in the setup and can take the majority of your setup time, this feedback can give you a general sense of how much time or effort it'll take to set up a simulation study with the current model. Let's go back to SOLIDWORKS and step through this particular utility. Here we have that cardan joint model, and if you go over to the Evaluate tab, we can invoke interference detection. Now make sure that the top level assembly is selected there for the selection box, or if you have a subset of components you wanted to check, be sure you select those in the selection box. Once we click Calculate, the software will go through and detect the interfering bodies. In this case, we have a bit of interference between the toolbox bolts and the nuts. At that point, we can decide what to do with those and then come back and check for the interference once again. Also, like I mentioned earlier, if you wanted to see how many touching face pairs there were to be addressed in the simulation study that you're about to do, I can ignore these particular interferences by clicking the Ignore button. And then down below under Options, I can click Treat Coincidence as Interference, and then click Calculate once again. This will detect how many face pairs are actually touching and are a potential for me to have to add context to when I'm doing a simulation study. In this case, I have 22 additional face pairs that I may need to go in and apply context to when I'm actually doing the study. This will give me an idea of how much time it may take for me to run through and vet this particular setup and get it done. So that was the last tip for this particular webinar. Before we end with any questions, I just wanted to promote our dedicated GoEngineer YouTube channel. We post videos here very regularly, and we invite you all to subscribe and stay up to date with our latest uploads. We have a wide range of topics that are covered, including simulation, so definitely feel free to stop in and search our extensive archives. We also produce a blog on our website that's very active with many tips and articles with useful information regarding SOLIDWORKS and other technical topics, as well as fun projects our engineers have been doing with 3D printing and scanning. Go check it out. All right, with that being said, we'll leave this webinar open for any other questions we didn't get to. Let's take a look here. All right, well, thank you all again for attending and for all your questions. We'll welcome you back for any future webinars with us here at GoEngineer, and have a good rest of your day, everybody.